Okay. You're welcome to Enoch's videos. And today, allow me to talk about the history of the periodic table. I'm talking about the history of the periodic table. When you talk of history, many people fear history, but today I'm going to talk about the history of the periodic table. Before we can start on the history of the periodic table, I want you to know the following about the periodic table. One, it is made up of 4 blocks. We have the S block, we have the P block, we have the D block, and then also we have the F block. So you need to know those blocks. Then also you need to know that a periodic table is made up of columns and rows. The columns which we call the groups, and then the rows which we call the periods. That one you need to know. So when you talk of a group, from top to bottom, that is a group, that is a group. Then from left to right, that is a period, that is a period. So then the other thing that you need to know is that a periodic table shows the position of metals, non-metals, and metalloids. That one you need to know. And since you all know that, I want to take you to the objective of today in discovering the history of the periodic table. I want to tell you that the development of the periodic table took place over a number of years and has involved scientists from different countries building on the foundation of each other's work and ideas. So there's no scientist who has been independent. We have been depending on one another. And imagine, from different countries, we have scientists from Germany, we have scientists from UK, we have scientists from all over the world, all over the world. So we shall look at the 4 key scientists who have contributed to the modern periodic table. So we have Bruyn, who brought the law of triads in 1817. We have the law of octaves, which was brought in effect in 1865. Then we have the periodic law, which was brought in 1869. And then we have the modern periodic law, which was brought into effect in 1913, just recent. So this was brought out by Mosley. Yeah, so those are the 4 key scientists I want to talk about. It doesn't mean that these are the only ones who have contributed, but there are others, but these are the key scientists I want to talk about. So I'll begin with the first one, that is Bruyn, who brought the law of triads. This was a German chemist, and he discovered that elements such as calcium, strontium, barium had similar properties, and also that the atomic weight of strontium was approximately the mean of the sum of atomic weights of calcium and barium. So he classified this trio of elements as triad. And these are not the only triads that he found out. He looked at chlorine, bromine, and iodine. So when he gets atomic weight of chlorine and atomic weight of iodine, add them together, divide them by 2, he could get the atomic weight of bromine. So it was like, maybe there is something. So he classified that as a triad. He went on ahead to look at sulfur, selenium, and tellurium. So he did the same thing, and yeah, it was coming out. So he came up with the law. But was this law corresponding with other elements? Not all elements could fall in this law. So there was a problem. But these are some of the elements worked on. Let's look at some examples. I'll use this table which is down to give more clear details of what I'm trying to talk about. For example, lithium is 6.9, that is its atomic weight. Potassium is 39.1. So we are going to add the two together and then divide by 2 so that we see whether we can get the atomic weight of sodium. So 6.9 6.9 plus 39.1, what do you get? What do you get? So this is 46, that is 46. So 46 divided by 2, you get 23. So this is a triad. Then when we come to calcium, strontium, barium, 40.1 plus 137.3, what do you get? You get 177.4. I went divide by 2, the answer is approximately to 87.6. So that was also a triad. It is the same thing to these other elements. But not all elements could form triads. So John Berrien brought out this idea of triads, though it could not work on all elements, but yeah, it could work for some elements. So he went ahead also to compare the metals and nonmetals and say that it works in both metals and nonmetals. There are still trials in metals and there are also trials in nonmetals. So for the metals, these are the metals he worked on: calcium, strontium, and barium. And then nonmetals he worked on chlorine, bromine, and iodine. So yeah, so what do you have to say? The guy was right. The guy was right. So that was in his year and was accepted. I want to tell you that what happened during that time, surprising that the scientist community at that time did not pay much attention to this law. And the classification of elements into triads was limited to just a few elements. So sometimes scientists can let you down, can let you down. But he made a hypothesis suggesting that there was an inherent link between atomic weight and properties of elements. There should be some link between atomic weight and properties of elements. I want to tell you that this was an important step. It was an important stepping stone in the development of the periodic table. So you cannot rule out the law of triads, though it never worked for many elements, but this was our stepping stone. Okay. Let me take you to another scientist, New Zealand John. He brought the law of octaves. Those who play pianos, those who play guitars, when I talk of octaves, I guess you understand. Those who know how to sing, do, re, mi, fa, sol, la, ti, do. I guess you know what I'm talking about. So, this was an English chemist who discovered that elements were arranged in order of atomic weight, and there appeared to be evidence of a pattern with the properties of the elements repeated in octaves consisting of 7 elements, such that elements have properties similar to the 8th element above or below. Remind, I'm going to explain this. So let's briefly go to the octaves that each of you knows. Yeah, so those who know how to sing, they say do, re, mi, fa, sol, la, ti, do. Yeah. So he tried to place elements in specific groups in specific groups basing on the octaves, as we are going to elaborate more. Okay, let's look at his findings. When you look at the piano, let's say that this is the white button. This is, let's say, do, re, mi, fa, sol, la, ti, do. So he could link this do to this first do and say that this element here should be having similar properties with this other element. Then if you were to continue, let's say do, re, mi, fa, sol, la, ti, do. So all the do's in this piano could be put in the same group. So that was his idea. I don't know how you see how vague it was, but that was his idea. And we have several elements that were placed in such groups. And let's try to look at the clear analysis of how he had these elements arranged. So remember, elements originally were being arranged based on atomic weight, only atomic weight. So if all these elements are arranged according to the atomic weight, he could count from 1, let's say, to 7, 1 to 7, again and again, and then combines those elements together. Let me give you an illustration. For example, in this case, let's say this is 1, 2, 3, 4, 5, 6, 7, 8. So lithium and sodium will be placed in the same group. Why? Because when you count 8 steps from lithium, you land on lithium and on sodium. So lithium and sodium could be placed in the same group. Let's look at beryllium. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8. So beryllium could be placed in the same group with magnesium. That was his idea, the law of octaves. You count 8, and then that 8th element should be placed in the same group with that particular element from where you started from. That was his idea. Let's check. Let's check on boron. So from boron, this is 1, 2, 3, 4, 5, 6, 7, 8. So boron and aluminium in the same group. Wow. Wow. Then we have carbon. Let's check carbon. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. With silicon. So that was New Zealand's discoveries. So it was all about counting. First of all, elements are arranged according to their atomic weight, and then counts 8, 8, 8, and piles and compiles and comes up with a group. I guess it is quite interesting. So his idea, okay, that was his idea, and then he had to take that idea to the scientists, and they had to look into his idea and find out whether it is really working out. So he came up, he actually compared elements in specific groups, but what were the difficulties? Let's look at the table that New Zealand came up with using the law of octaves. When you look at some of the elements were placed in more than one element, could be linked or placed in a specific group and a similar period. What do I mean? This is what I mean. For example, when you try to locate cobalt and nickel, all were placed in the same position, and this couldn't be allowed. How could two elements occupy the same position? This was really prohibited. So scientists looked at his ideas and say, no, we cannot accept this. We cannot. Then they looked at another group, they saw more than one element present. They said, no, please, New Zealand, we are not accepting your work. New Zealand felt so annoyed. They tried to prove to him that he was wrong. What did they do? They went on to look at the properties of the different elements in specific groups. For example, let's look at copper. Copper is in the same group with potassium, sodium, and lithium. But you need to know that sodium, potassium are highly reactive elements. They're highly reactive elements. But copper is not so reactive like these elements in the same group. So they told him, no, there's a problem with your findings. We shall not accept them. We shall not accept them. This guy in New Zealand was working as a chemist on one of the sugar factories. He was a chemist there. So he came up with this work, but scientists looked at his work and they mooted it. They mooted it. They said, no, your work is not really coming up proper. It doesn't match. It doesn't match. So New Zealand felt very bad, and went back to work on the sugar factory. So what do you have to know about New Zealand's ideas of octaves? One, they were only limited to a few elements. Then also you need to know that he tried to apply this principle to the known elements, about 60 at the time. However, they did not neatly fit in the type of the pattern. Then also you need to know that highly reactive elements such as lithium, sodium, potassium, rubidium, and cesium became grouped with unreactive metals such as silver and copper. That was really unrealistic, and therefore the scientists told him, please, New Zealand, go away. We shall not accept your work. Come on, go and make more research. Was satisfied. Wow. New Zealand presented his law to the Chemical Society in England, but his ideas were not accepted. So as a result, after feeling so much being ridiculed, he went back to his position of chief chemist at the sugar plantation. So that's what happened. Sometimes I think we need to treat people fairly, otherwise we may prevent research to take place. Now let me talk about the manlys who brought the term called the periodic law. In 1869, that is 4 years after New Zealand's ideas were first mooted, this Russian discovered that these elements, although they are arranged according to their atomic weight, but there is a relationship between atomic weight and their properties. There is a repeated pattern of properties. There is a repeated pattern of properties. So if there is a repeated pattern, so he came up with a law and called this law the periodic law. Remember, it's linking atomic weight with properties, but these properties keep on repeating themselves. So he tried to arrange elements, one, according to the atomic weight, and then also linking those different atoms with their properties. Because remember, those properties kept on repeating each other. So he came up with an idea and said, no, let me try. Yeah, so he tried his best. And what did he come up with? This is his work, which I want us to look at briefly. So Manlys improved the table over time, and he left gaps for undiscovered elements. That is, the elements whose properties could be easily predicted but were not in place. So he left gaps so that each element fell into the correct group. Manley was bright. I think he was bright like me. So using this approach, Manley was able to predict the existence and the properties of undiscovered elements. You can imagine, you could tell the future of a given element that would fall in a specific gap. However, I want to tell you that some elements did not obey Manley's version of the periodic law. For example, iodine. Its atomic weight is 126.90. He placed it in the table after terrarium, despite the fact that terrarium had a high atomic weight. So it couldn't match. So at a certain point, he failed to match the atomic weight with the properties. But yeah, his work was better than New Zealand's work, because for New Zealand, at least, sorry, for the problem with New Zealand, you could combine more than one element in a specific area or position, which Manley never did. Then we come to our last scientist, that is Henry Mosley. Was born in 1887 and died in 1951, just recent, a few years back, about 105 years back. Yeah. So these scientists saw that there was a problem with atomic weight, because every person complained about atomic weight. So what he did was to arrange, first of all, the atoms according to their atomic number rather than arranging them according to their atomic weight. When he did that, everything was sorted. Everything, I'm telling you, was sorted. He's the scientist who arranged the atoms. Is the scientist who arranged the elements in the periodic table basing on their atomic numbers. And now we have the modern periodic table. We have the modern periodic table. Oh yes. So now, after having that modern periodic table, different groups were assigned different names. Let's look at some of the groups. For example, group 1 was referred to as the alkali metals. Group 2, alkaline earth metals. Group 15, the pictonogens. Group 16, the chalcogens. Group 17, halogens. Group 18, the noble gases. What a wonderful work that was done. This was wonderful work. So now we have the modern periodic table. We have the modern periodic table with showing clearly the non-metals, the metals, and the metalloids. Clearly, everything is clear. And this is now what we call the modern periodic table. I want to tell you, and I want to remind you that the horizontal laws of elements numbered from 1 to 7 are termed as periods. The period number is equal to the principal quantum number n of the highest occupied energy level in the element of the period. We shall talk about that in the next coming lessons, but you need to know that. Then also you need to know some key facts. 1, my contact. In case you need details about the history of the periodic table, I can come and discuss more with you. However, not only the history, but even the chemistry itself. Yeah. Love my videos, share my videos, subscribe to my channel so that you can get updates of the new videos. Thank you for watching Enoch, the chemist of 2020. Share, and don't forget to contact me. I wish you a nice day.